Alright, so we will continue on today. And did last week's homework go okay? Stuff on the normal distribution? That was alright? Yes,
I asked a question on the Facebook site about
okay, I'm sorry.
annotating.
Yeah, I probably didn't respond. Yes. What was your question?
Well, because on your instructions you said that we should annotate, and on this, I wasn't too sure what you wanted other than just the
Yeah, you could use either the pound sign to just basically at least just say like this, because sometimes I just get like a whole bunch of computer output. At least break it up and say, this is the answer to this problem.
Oh, so you just wanted it like separated A, B, and C, or
kind of.
if it's like continuity, separated from with and without.
Something like that, exactly.
But we didn't have to like break everything down.
No, you didn't have to tell me this. Yeah, that defeats the point of using the computer. So. Okay. Sorry, I didn't get back to that.
So you weren't supposed to do it all manually and write it out?
I'm sorry?
On the lab part?
Yeah.
Did you want us to do it manually and write it all out?
I'm not sure if I understand your question. Because you did it by hand as part of your homework assignment, right? So that would be the manual part? That's all you had to do, yeah.
Did you want us to print out what we got from the computer, from that program, from R?
Well, you had to turn in something, so I figured you printed something from there.
I didn't print that one out, but I wrote it. I turned in my homework.
Okay, I'll take a look. I'm sure it's fine. Alright, and then you guys just got your quizzes back. If you have any questions, you can let me know. 30 points max. I don't know if it's necessary to curve anything yet, but we'll just leave it at that, and then if curving is necessary, we'll take that into account. But okay, so today we move on into Chapter 5. Chapter 5 is on sampling distributions. Okay, before we get into sampling distributions, we just want to go back and talk about the normal distribution, which describes a random variable for many different things in real life, where if we picked a random person, the height, even though we have no idea how tall this person is, we expect this person's height to come from the normal distribution, where average height is the most common, and people who are far above average would be less common but possible, and people who are far below average, also less common but certainly possible. In Chapter 5, we're going to be dealing with something called a sampling distribution. This is different from the distribution of a random variable in that here we are dealing with distribution of samples, sample statistics. Okay, so here is here I've got an ordinary deck of cards, 52 cards in it. If I pick a card at random, what are possible values that I might draw?
3 of hearts.
Huh?
3 of hearts.
3 of hearts, right? Okay. So the smallest, if we just label them, if we say ace is worth 1, all the way up to king 13, okay? Each card has an equal probability of being selected, right? And the smallest would be from 1 to 13. So I can shuffle these cards, and I can draw a card at random. So what would the distribution of possible values look like? If I drew a plot to show you what the probability distribution looks like, what would that look like? What do you mean by linear? So again, yeah, as you said, here's one number, it's a queen, so I drew basically a 12. Okay, if I put that back and I shuffle it.
You're saying what's the probability of picking any of those cards?
No, I mean just what would my probability distribution look like? The graph. Is this question not? Here I drew a 9. Okay. How can I show that? So here I'm drawing a card from a deck. Okay, basically, there's 13 possible values, right? Okay, basically 1 through 13, each are equally likely. Okay, so what does my probability distribution look like? Okay, so technically, it's discrete, so I'm going to just make a number line. 1, 2, 3. Basically, this goes the opposite direction. Okay, so my probability distribution, what it looks like is probability of drawing a 1 is what? Not 0.
4 out of 52.
4 out of 52 or 1 out of 13. Okay, so the height on this axis right here, this is 1 out of 13, whatever that number is. Okay.
It's just linear.
Yeah, and then I can draw 2, a 3, so it's just a flat thing indicating that each of these values all have the same probability of being drawn. Okay, but nothing at 14, nothing at 15, nothing anywhere else. Okay, sometimes the book will, different textbooks will put a vertical line to kind of make these more visible. But whatever, it's all the same. Okay, so this is what the probability distribution looks like for drawing from a deck of cards. Okay, what if I didn't deal with individual cards? What if I drew 5 cards at a time? Okay, so I deal myself 5 cards. 1, 2, 3, 4, 5. And instead of looking at the individual values, I'm going to just say, take the average of the 5 cards that I deal myself. Okay, so I deal myself 5 cards. And technically, I shouldn't do. Okay, maybe this is a little bit different. But imagine I draw myself 1 card, okay? But I'm going to draw 5 cards. So I draw 5 cards, but with replacement. Okay. So the first card I draw is a 4, and then I put this back in the deck, and I shuffle it, and I draw another card, and the next card I get is a 6, and then I repeat this process, shuffle it back in the deck, and I draw another card. Here I got an ace, so that's a 1. I put it back in the deck and I mix it up, and then I draw another ace, back in the deck, mix up, and I draw a 9. Okay, so this is one sample of 5 cards drawn at random from the deck. And I take the average. I'm going to find my Y bar for the sample, so I have 10, 20, 21 divided by 5, 4.2. Okay, and let's say I do this again. I draw 5 cards at random. So here I got a 9. Put that back in the deck. Mix it up. Then I draw a 2. And then a queen, which is a 12. And then a king, which is 13. And then a 5. So what does this thing look like? So the average of this is 25, 30, 41. Y bar is, I think, 8.2. Not mistaken. Okay. And so let's say I repeat this over and over and over again. Okay. What are possible values of Y bar that I might see? Technically, Y bar can take on any value from what to what?
1 to 13.
1 to 13, right? It's possible for me to draw 5 aces, okay? That's possible, and my Y bar would be 1. And it's also possible that all 5 cards I draw are kings, right? Especially if I'm doing this with replacement, and Y bar would equal 13, okay? But how likely is this number compared to this? How likely am I to get Y bar equal to 13 versus Y bar equal to 8.2?
Less.
This is much less likely, right? Like, there's only one way for this to happen, to get 13 as the average. And there's probably a whole bunch of ways for me to get 8.2. Okay?
Aren't there only 4 of each?
Yeah, but
Yeah, but I'm doing it with replacement. So I'm putting it back in and shuffling it up and pulling a card out. Okay? So here, what would the probability distribution of my Y bars look like?
Standard.
Okay, so let's distribution of the Y bars look like.
Good standard bell curve.
Okay, is it a normal distribution? Is that what you're saying?
Yeah.
Okay, and yes, the answer is okay. So technically, because this thing is discrete, all right, and here I'm drawing only 5 cards at a time. Like, I'm only gonna see 4.2 or 4.4 or 4.6, 4.8 or 5.0, right? I'm not actually gonna see 4.1 or something because I can't. There's no combination of 5 cards that will give me an average of 4.1. Okay, so that's kind of a technicality, but if I just kind of approximate it with a curve, it would look kind of like the normal distribution. Yes.
Do we know that it follows a normal distribution because all binomial distributions follow a normal distribution?
No, this isn't even a binomial distribution. It's
Okay.
It's almost like a uniform distribution, but it's a discrete uniform.
So is there a way for us to know that it follows a normal distribution?
No, you guys could just kind of. It was a suggestion, and that happens to be true. We'll talk about exactly because it's not always true. It's not always true. But we're gonna get something that looks like the normal distribution. It's technically not because it's still a tiny bit discrete and things of that nature, but it's something looks like the normal distribution. where the most common number that I'm going to see is going to be kind of right in the middle, right around getting an average of 7, okay? 1 plus 13, basically the middle number. So with 7 being kind of the most common total that I'm going to see, and totals around 7 to be quite common, where totals that are vastly different from 7, so the smallest, so it's not a true normal distribution because it's still discrete and it doesn't go to positive infinity and negative infinity, okay? But getting a total of an average where the total average is 1 would be quite rare, and getting an average, a sample of 5 cards where the average is 13 is also quite rare. Okay, and so we have, this is kind of what our sampling distribution looks like, okay? And again, what is this a distribution of? Yeah, this is the distribution of the y bars of each of my samples, okay? So this is the distribution of y bars from the sample of 5 cards. And this is the basic premise of sampling distributions, okay? We went from, this is basically the population from which we are drawing cards, is this uniform distribution where all the numbers that are possible have equal probability. But if we draw 5 numbers at a time, or 5 cards at a time, we see that 13 doesn't have the same probability of showing up as, say, 7.2 or something like that. I just want to make sure everyone's okay with this, all right? And that's because to get an extreme value like 13 or 12 or 13, that means the average of all 5 numbers has to be up here. So all 5 cards have to be kind of in this high range. Whereas to get an average around 7, sure, you can have a card low and a card high that kind of cancel each other out and brings you towards the middle. Okay, so let me just kind of put this into maybe a more generic and abstract form. Is that here we have some population, and from the population we take a sample. Population has parameters mean, mu, and standard deviation equal to sigma. These are just things about the population. And our sample has a mean y bar. And the sample comes from, has size n. Okay. Okay, so y bar can take on basically any value. And let's say we repeat this, okay? So we draw another sample. Again, with size n. And this time, I guess here I'm gonna label this y bar 1 to indicate that it's the mean of that one, and this is gonna have mean y bar 2. Okay, so it's also the average of the endpoints in this sample, which may not necessarily be the same as the average of this sample. Okay, probably won't be. Okay, and then let's say I repeat this again and again and again. Okay, so I take a whole bunch of samples over and over and over again. Each time getting calculating the y bar. All the way to the y bar of the last sample. So I've got, let's say I repeat this many, many, many times, okay? So thousands and thousands of samples of size n coming from the population. Alright? The sampling distribution is what is the distribution of the different y bars that I might see. That I see or might see. So a lot of this, the answer here basically depends on the population and the size of the sample. Okay. Because if I'm only drawing, like let's say we're dealing back with this deck of cards, if I only draw 2 cards at a time, okay, then I wouldn't have a normal distribution. It would actually look kind of like a pyramid, where, because there would be basically 13 ways to get the average of 7. Okay, 1 and 13, 2 and 12, and so on and so forth. Okay, and there would be 12 ways to get an average of 6.5, and 11 ways to get the average of 6, and so on. And it's just kind of, I guess, a little bit more linear. But anyway, let's go back to this. What is the distribution of y bars that I see or might see? This is called the sampling distribution. Okay. Okay. And under certain conditions, the sampling distribution of y bar, sampling distribution of y bar will follow the normal distribution. Or close to it. And I write the sampling distribution of y bar because we could have the sampling distribution of, let's say, S, the sample standard deviation, but it wouldn't follow the normal distribution. It would be something else, right? If for each sample I calculated the standard deviation and I did this over and over and over again, what would that sampling distribution look like? That would be something else. But here we're dealing with the mean of each sample. Okay. Is everyone following me so far? Any confusion here? Okay, good. So I wrote, under certain conditions, the sampling distribution of y bar will follow the that's known as the central limit there, okay? So the fact that sampling distributions, is basically sampling distributions of y bar follow the normal distribution under certain conditions. Okay, so what are these certain conditions? Okay. The first condition, which is kind of what goes into a sampling distribution anyway, is that the samples are selected at random, okay? Truly randomly, okay? Not in an arbitrary manner, but in a random manner, okay? And I guess the other part is that probability of being selected is independent. So probability of any individual being selected is independent of other individuals, okay? So we're picking individuals at random, not like we're going to take this whole family together, okay? Because I guess technically that's still random, but now the entire family got selected together. That doesn't work. Okay, so that's kind of necessary for sampling distributions anyway. All right. The second condition is that the sample we select is not too big, okay? If we're selecting without replacement, our samples cannot be too big, okay? Not be too big. And too big is more than 10% of the population. And if you select with replacement, then it doesn't matter. Okay. If you select with replacement, it doesn't matter. But if you select more than without replacement, okay? So, like from this deck of cards, if I'm selecting several cards at the same time and not putting them back in the deck, then I can't sample more than, I shouldn't sample more than 10% of the population. Because when I do that, then this condition actually gets violated. Probability of each individual remains independent, okay? So if I start off the deck with 26 red cards and 26 black cards, once I select 5 cards, if, let's say 5 of them happen to be red, okay, then what remains is not 50% red, 50% black. I have more black cards than red cards, and so the probability of selecting a red or black card is no longer independent. Okay, but so this one rarely gets violated, okay, just because we generally don't run into the problem of we have too much data, okay. So the last one is our sample cannot be too small, okay. So we can't have a sample that's too big, and last one is our sample cannot be too small. But that's two things that go into this. Okay, one, if the population is normal, or nearly normal, nearly normal meaning unimodal and symmetric. Small samples are okay. Small being like samples of size 5 or 4. I guess even if it's truly a normal distribution, even samples of size 1 will come from a normal distribution, right? And samples of size 2 will definitely will also come from a normal distribution. So if the population is normal or nearly normal, small samples are fine, no problem there, okay? If the population is not normal, we need a larger sample. And this is a very vague and arbitrary rule, okay? Larger sample. Where the more non-normal it appears, I guess the key here is the more non-symmetric it is, the larger your sample it needs to be, okay? So the more non-symmetric, the larger the sample needed, okay? So, the size, okay. If it is very non-symmetric, very large samples might be needed. Rule of thumb is that for most situations, a sample of 30 is usually big enough, okay? But if it's very non-symmetric, like extremely skewed, then 30 will still not be big enough, okay? Samples of size 30 are usually big enough. For number 3. Okay. And other times, if it's really skewed, you can try to do a few things to it. Like you can take the log of all the numbers rather than dealing with the numbers themselves to kind of put things into a more general sense if they're really skewed. So taking the log can help, or taking the square root can make things that are very skewed into things that are less skewed. Sometimes log transformation can also help. Okay, but that's kind of an aside. Alright, is that okay? The conditions that are needed for us to use the normal distribution. Okay. So let's try something out. So then y bar comes. So if these conditions are met, okay. y bar can be said to come from a normal distribution where the mean is equal to the population mean. So in other words, the mean of the sampling distribution is equal to mu. And the standard deviation is equal to the standard deviation of the population divided by the square root of n, the sample size. So standard deviation is equal to sigma over the square root of n. Okay. So remember, here we're taking samples of size n of the population. And what this means is that when we do that, the mean of our sampling distribution, the y bars, themselves come from a normal distribution with the same mean as the population, but the standard deviation is sigma over the square root of n. Okay? So larger samples, if we take larger samples, what happens to our sampling distribution? The spread shrinks, okay? With larger samples, larger size samples, if we increase n, the spread of our sampling distribution shrinks and gets smaller. Okay? So let me do a little computer demo here. So the histogram at the top represents our population. Okay? So the population has mean 16 and standard deviation equal to 5. Right? And what I'm going to do is I'm going to take a sample of size 5, okay, from the population distribution. And what you're going to see is you're going to see the computer randomly select 5 values from this normal distribution. Okay, so the most common values will be in the middle, but of course the values that are away from the middle will also happen. Okay, this represents one standard deviation above and one standard deviation below. So approximately what percentage of the data is within one standard deviation?
68.
Okay, about 68%. So about 2/3 of the data, generally, rule of thumb is about 2/3 will be within the red line and about 1/3 outside, okay? I'm drawing 5 at a time, so we'll see. We'll see how true that may hold. Okay. So here's 1, 2, 3, 4, 5. Okay. And so it took here the 5 numbers that it drew, and it calculated the average. This blue dot right here, or blue line, represents the mean of this of these 5 numbers, and it plots the mean right here. Okay, so it's going to build up a histogram down here of the different sample means that it observes. Okay, there's another 5. Here's another 5. Alright, and so we're slowly building up different, okay, so each time we're calculating another y bar, and then we're plotting it down. Okay, so this is going to take a little while. Alright, so now I can just do a whole bunch at a time, and we can see our histogram slowly building up. And right now, it seems like the shape is weird. Okay, so this is after about 500 total samples. Now we're starting to see the normal distribution appear, okay? So law of large numbers says that when we do something a whole bunch of times, it approaches the theoretic probabilities, right? So we just have to do this a whole bunch of times. So I just do okay. So this is after about 36,000. Okay, it looks very normal here. Okay, and we can calculate the mean of all of these numbers and the standard deviation. Okay, and here the mean is 15.99, so about 16, right around the population mean of 16, and the standard deviation is 2.24, which is going to be 5 divided by the square root of 5. Okay, and you can verify that. If I take larger samples, okay, samples of n equals, let's say 10, it's going to clear this out, and again, here I'm taking 10 numbers and finding the average. And I'm going to slowly build up this thing here, okay? I can do it over and over and over again. Okay, and so we see after we do it many, many times, this thing also looks like the normal distribution. The mean is, again, right around 16, and the standard deviation here is 1.58. Yes?
For the means to follow a normal distribution, does the parent population have to be like a normal distribution?
No.
Okay.
Well, yeah, so not, yeah. We talked about when the parent population is normal, any size sample will create this thing to be a normal distribution, right? That's the central limit there. So now we could try it with things that aren't the normal distribution, okay? So here is a uniform distribution. So this is kind of like a deck of cards where you can get any value from 0 to 32. They're all equally likely. So if I take a sample of size, so here we can see if I take sample, here, this is samples of size 2, okay, with the normal distribution, and we're just taking 2 numbers, and we're plotting it and over again, and we can see that even with samples of size 2, we get a normal distribution down here, okay? If I do this with the uniform distribution, samples of size 2, and if I plot this over and over again, just drawing 2 numbers at random, and I do this many, many times, okay, I can build this up, okay, this is not the normal distribution, okay? It looks like the pyramids of Egypt. And that just shows us that the mean is 16, and that's the most common number, but the shape is clearly not normal, okay? But here I can start doing, samples that are a little bit larger, samples of size 5. Same idea here, just draw 5 numbers at a time, we calculate the average, and we plot that, and we build this histogram up. Let me just do kinda. So even with samples of size 5 and the uniform distribution, I get something that looks kind of like the normal distribution, okay? And up there we can see the standard deviation of that thing is 9.52, and this is going to be 9.52 over the square root of 5, which is 4.25 there, okay? Samples of size 5, and I can do this. I can take even bigger samples. That's drawing 10 numbers and averaging them. And then with samples of size 10, we see also, again, normal distribution, and this time the spread is even smaller. Okay, and we can try it with a skewed distribution. And again, if I take a small sample, and I do this over and over again, we're going to see that most of the numbers we see that when I take small samples of size 2, this doesn't look anything like the normal distribution, okay? It fits, it's less skewed than that, but it's still, we still have some problems here, okay? But the normal definitely doesn't describe that. Okay, so I can take larger samples, again, drawing 5 numbers at a time, taking the average of those 5 numbers and plotting them. Okay, and we can see this looks a little bit better, okay? The mean is right around the same as the mean of the population. The mean of the population is 8.08. Here the mean is 8.07. And we see the standard deviation has shrunk. And so this part looks kind of normal-ish, but we also see we still have this tail that exists that kind of throws things off, okay? So in order, and we probably won't ever fully get rid of that, but when I take larger samples, okay, we'll ask the computer to do this over and over again, okay? This thing looks a little bit more normal. There's still kind of a little bit of a tail, but it's not as bad as it used to be. And we can see that even though the population is clearly not normal up here, when I'm taking averages of large samples, so here's, I'm taking samples of size 20, okay, the sampling distribution of y bar ends up looking a lot like, or ends up basically being the normal distribution. Okay. And it works even with, crazy distributions. So you can, so one of these, you can kind of draw a distribution here. So I can do something like this. All right, and if I take samples of size 2, we can see, we're going to have all sorts of problems here. Okay. This is clearly not the normal distribution. What you're seeing here is you're seeing a peak when both numbers come from this side, a peak over here when both numbers come from this side, and then also a peak in the middle when one comes from that side and one comes from that side, okay, when I'm taking samples of size 2. But then when I take bigger and bigger samples, okay, we can see that with samples of size 5, it starts to look normal, and then by probably around 16, it looks pretty normal, even though the population itself looks very not normal, okay? Alright, so this is sampling distributions, the idea that we have some kind of population with a mean and standard deviation, and when we take samples from it, if we don't look at the individual values, but we look at the mean of those samples, and we create, you know, what are the possible sample values that I observe, that ends up following the normal distribution. Yes.
So, is one of the reasons why the sample distribution follows the normal distribution because we're building a new model based on the mean? Does that question make sense? So that if everything's built around the mean, it would be unimodal no matter what the population looks like?
Yeah, that's what the central limit theorem states, okay? It says when you have a population and you're taking samples from that population and just calculating the mean of those samples, that sample mean will follow the normal distribution as long as those conditions are met. As long as those conditions are met, okay? And we saw that, you know, when we took small samples like n equals 2, alright, it didn't look like the normal distribution. That histogram at the bottom didn't look like the normal distribution. But even though the population was very strange shaped in terms of its distribution, when we took large samples, it looked normal. Okay? And so if you're asking why that is, I don't think I can give you a good answer here. If you want, you can take a mathematical statistics class, but that was like my least favorite statistics class. Okay. Maybe in this class it's okay to just say this happens. All right. You know, we did it with the computer. Maybe we don't fully understand why, but it happens. Okay. And that's actually how a lot of statistics is done today. We say, you know, maybe we don't, because at a certain point, the math questions get really hard to answer, mathematically. And so we say, you know, we don't exactly know why it happens, but we can repeatedly reproduce this with a computer, and it definitely happens, so we will accept it as that it happens. Which I guess is okay. All right. So let's try an example. Okay. So remember that when we're dealing with the sampling distribution, our mean is mu, and our standard deviation is sigma over the square root of n. Okay. So let's say IQ scores come from the normal distribution with mean 100, standard deviation 16. Okay, so I'm going to ask you a couple questions. All right, I'm going to say, what is the probability that a randomly selected person has an IQ of 108 or higher? Okay, and then the next question is, I take a sample of 8 people. What is the probability that their average IQ, I should say I take a random sample, average IQ is 108 or higher. So go ahead and try that. Probably need your normal distribution table. You have it, or at least, if you don't have your normal table, at least figure out the z-scores that you would use to look up using normal tables. You guys need another moment to get the answer? Okay. Okay. Alright, so the first one, what's the z-score that I'm going to look up?
0.5.
0.5, right? So here my IQ is 108, or the IQ that we're looking for is 108. I subtract out the mean of 100 divided by 16. My z-score is 0.5. I look that up in the z-table, and I get 0.6915, and that means this side is going to be 0.3085. Okay, 1 minus that. Or I can just look up z equals negative 0.5, and I'm going to see 0.3085. Okay, and then, but here, now I'm taking a random sample of 8 people. What's the probability that their average IQ is 108 or higher? So here I'm asking, what's the probability that y bar is greater than 108? Okay, what's the probability that y bar is greater than 108? Okay, so y bar doesn't come from this distribution. That's the distribution of our population. Y bar comes from a normal. What's going to be the mean?
100.
100, and what's my standard deviation? 16 divided by the square root of 8. Okay, so this is some other number, 5 point whatever. Okay. So now that I have that, I could do 108 minus 100 divided by 16 over the square root of 8. And my z-score here is going to be 1.41, if I did my math correctly. Okay, and then so when I look up 1.41, I can find the area to the left and subtract that from 1, or I can look up negative 1.41, and then I see the area in the tail is 0.0793. Yes?
Do we need to apply the continuity correction here?
No, there's no continuity correction to apply here. Okay? Why is there no continuity correction to apply?
Because the scores are determined.
Yeah, because to begin with, IQ scores are continuous, okay? And then when we say we have a sampling distribution, our sampling distribution is normal, which is also continuous, okay? So we only apply the continuity correction when we're using a continuous distribution to approximate a discrete distribution. Here, there's nothing that's discrete, so there's nothing to worry about here, okay? So we don't need to apply any we don't need to add 0.5 or subtract 0.5 to anything, okay?
So how did you add 0.0793? Is that one? Yeah, 1 minus.
So when you look up 1.41, what is the number you find again?
0.9207.
Yeah,
Okay.
right? 0.9207. Okay, but I'm asking average is 108 or higher.
Yeah, I got it now.
So I'm going to do 1 minus that, and I get that. Okay, so 8%. So here, it's the same number, 108. When we're looking for an individual, there's like a 31% chance that a randomly selected person has an IQ of 108 or higher, right? But if we're selecting 8 people at random, the probability that all 8 of them have an average IQ of 108 or higher now drops down to only about 8%, okay? 0.0793. Okay. What if I want to do this in R? What would I do? How would I get? How do I get 0.3085 in R, or something rather? I'll give you a hint. I'm going to use P norm somewhere in there.
1 minus P norm, parenthesis.
Yeah. So I would do. Well, it depends what you want to how much you want to type.
And then
Okay.
the standard deviation.
So if you know your z-score is 0.5, you can get 0.3085 if you type in 1 minus P norm, P norm 0.5, okay? Or if you didn't bother calculating it was 0.5, you can do 1 minus P norm, 108, 100, 16.
Yeah.
Okay? That's how you can get that one. Alright, so then how do we get this one? 0.0793. I would do what? 1 minus P norm 108, 100, and then I would do what? 16 divided by the square root of 5. Or bothered figuring out this number, you can do that also. I'm sorry, square root of 8. Square root of 8, sorry. Just kidding. Yes?
I mean, the way okay, I must not have known that shortcut. I had to do, you can do caret 1/2, right?
You can do caret 1/2.
Okay.
Yeah, that's also the square root, okay? So you can do 16 divided by, and then you're going to have to put that in parentheses, 8 caret 0.5.
Yeah, okay.
Okay.
The square root also works?
Square root, yeah, SQRT. SQRT. Yeah. The basic functions, you can just, Google search, or whatever favorite search you want to use. Just do R operations. Operations or R operators. And that shows you how to do multiplication and division and square roots and things like that.
Square root is that caret 0.5? That's
Caret 0.5 or SQRT, whatever number.
square root.
Okay. I'm used to typing SQRT, parentheses, but caret 0.5 is the exact same thing, right? I'm just trying to think if there's ever a situation where square root is not caret 0.5, but there's not. It's exactly the same. Okay. Is that all right? The R commands also.
Yeah.
Okay. How was using R?
That's fine.
It's fine. You loved it or you hated it? You hated it.
Okay.
Alright, I'm sorry. What was the worst part about it for you?
I think I was just having difficulty on what I was supposed to enter. As far as like doing the T binom, and what I was entering, and then at first I was putting spaces and it was just constantly giving me errors.
Okay, yeah, don't.
It was those kinds of little glitches that were driving me nuts.
Okay. Alright. Oh no. Okay. Have you ever done any kind of computer language or programming before? Okay. Yeah, anytime you try to do computer language and programming for the first time, it's going to be very frustrating because the computer is very stupid in that it needs things to be an exact certain way, otherwise it freaks out, okay? It's like dealing with the most literal person ever. And you can't use any kind of figures of speech or any kind of whatever, yeah, so or entering a foreign country where you have just a rudimentary grasp of the language and you're trying to give instructions to do something. The first time is always frustrating, and I hope it didn't make you hate all computers ever, but it gets better.
This is gonna be kind of silly, but on that table, you know how like you look up the z-score with this? What are these values actually called?
What are those called?
Like just
No, if they're called areas.
areas?
Yeah, areas.
I mean that makes sense because it's the area under the curve.
Yeah,
Alright.
areas are probabilities. Okay.
Okay.
I guess. Yeah, it's a good point. Okay, so basically the z's go, in this column, and technically what appears here is the probability that that z is less than or equal to the z that you look up. Okay.
Yeah, that's why I was trying to write it out and be like z tells you what the probability is up to that point.
Yeah,
and so I was gonna say
it's the probability that z is less than the z score.
Right. But so you would really just say that the area. Okay.
Yeah.
Okay.
Yeah, we're going to deal with something called the t-table, which works totally differently later on, but not today. I don't think. Maybe. Oh, we do use it today. I'm sorry. Okay, is that all right with sampling distributions? Okay, we'll take our break a little early, and then when we come back, we'll talk about the application of sampling distributions here.